Hello everyone, my name is Hasna Fauziyah, and let me start this with a very simple question. What usually causes machines to fail? Is it control system or something more basic? But if I tell you that the problem is often bearings, what happens inside the bearing during operations? Under repeated loads, the surface slowly degrades. Micro cracks appear and then eventually failure happens. So how do we detect it? What if the answer is hidden in the signal? Because at stage 2 and stage 3, the damage is already there, but nothing looks wrong visually. But subtle change in vibrations appear long before catastrophic failure. Now let's take a look into the impact. Why does this matter? Because bearing failure causes around 40 to 50% of rotating machinery failures, and in some electric machines, up to 75. So here's the real questions. Do we wait until its failure happens, or can we detect it or predict it earlier? This is the motivations of this study. And let's continue with another question. What if we place a vibration sensor in a machine while still running normally, and then we get raw data of vibration signal, messy and hard to read by humans. So the next question is, can human analyze this data continuously? Probably not. So what if the machines analyze machines? What if we feed our vibration data into a machine learning models? What if the output is not just fault or no fault, but remaining usable life? Not something is wrong, but how much time do we still have until it's failed? Now, the bigger picture, why does this matter for industry? Because this turns maintenance into a decision tool, not reactive but predictive. What do we gain from this approach? Higher reliability, lower downtime, and maintenance costs. And where does this fit in Industry 4.0, digital twins, smart factories? So the purpose of this study is very simple, to use a vibration data and machine learning to predict bearing failure earlier and support predictive maintenance decisions. So how do we actually do this? We use a raw vibration signal from NASA IMS bearing datasets and then segment the vibration data into fixed time windows, and then make it suitable for learning. And then we extracting the features for domains, time domains, including yaw parameters, frequency domain features, including FFT indicators, and spectral shape, and also band power features. And then we get initially 30 features, and then reduce it into 17 by forward selections. And then we train and test with random forest multi-layer perception models. We evaluate the result by comparing predicted ROL and actual ROL using standard statistical metrics and AKK information criteria. So what do the results tell us? The random forest models show a strong alignment between actual and predicted ROL. The points follow the diagonal closely. This means high prediction accuracy, while on the other side, the multi-layer perception show larger dispersions and higher predictions error. So the next question is, which model is more reliable? Let's take a look into the numbers. Random forest achieves lower MAE and RMSE, higher R square and lower AIC. What does lower AIC mean? A better balance between accuracy and model complexity. What about stability? The residual plot of random forest is more centered and more evenly distributed. This indicates more stable prediction across the entire ROL range. So what can we conclude? Can we reduce the model complexity without losing accuracy? Yes. Forward feature selections reduce 30 features into 17 while keeping high predictive performance. Which model looks better? Random forest outperforms MLP with lower error and higher R square and more stable residual behavior. Why does this matter? Because it offers a lightweight, interpretable, and accurate solutions for vibration-based ROL predictions. Where can this be applied? As a core component in digital twin-enabled predictive maintenance, supporting better maintenance planning and reduce unplanned downtime. Thank you, and I'm happy to take any questions.